Anyone? All right. So yeah, the plan is to go through these slides front to back until people can't take it anymore. So thank you for all coming to this. I was planning probably only an hour worth of material, but it's a significant body of work. So it'll be interesting to see how far we can get. So, okay. So what is it that category theory is just at a high level? So different people have different understandings of this. One thing that all these understandings have is that they're very algebraic. So category theory can almost be thought of as what happens when you take algebra super seriously. And in particular, what happens when you take functional algebras super seriously. And so the category concept itself was invented in an indirect way. Folks doing algebraic topology in World War II needed help essentially doing bookkeeping because there's all these continuity conditions and topology, and everything's very subtle. And it was category theory that they invented as a way to help them with their work there. And so it has since been appropriated first into, I'd say, logic and computer science, and now into other areas like biology. But unlike some other areas or most other areas of math, it's kind of has this meta-mathematical character that it's, although it originated in algebraic topology, the same abstractions that came up there, things like products and sums and Cartesian closed categories and all of that kind of stuff, it's found in other fields like logic. The same Cartesian closed category might come up as an interesting kind of topological space, but then also like a Boolean algebra type of thing. And so it very quickly became apparent to mathematicians that category theory was, you might even say, a meta-mathematical type of field. And so for that reason, it's often called abstract nonsense among mathematicians, although at its core, it's really no different than, say, group theory, just with different axioms, or set theory, just with different axioms. So anyway, it gets a lot of, it's often misunderstood for reasons that really have nothing to do with what it is, but more things like fashion and popularity and all of that. But anyway, I guess to elaborate on that, we say in category theory that it talks a lot about how things behave and not what they are, but, so does group theory, right? Like you define groups based on, how they behave, and they're defined up to isomorphism. And so it's really set theory that's kind of the weird thing, that it's only in set theory where you really talk about like how things are built. In any other area of math, you're kind of always working up to isomorphism and like working up to in a structure independent way. So anyway, that's probably why it's been so successful, category theory. I mean, you can't do like advanced work in computer science, at least some areas of it, like programming language theory, without using category theory. It's just seems to be better foundations than set theory. So anyway, and then of course, we like it in database land because of this direct observation that a database schema has the structure of a category theory kind of straight up. And so that's, we noticed that, or a lot of people noticed that, not just us, and then others are finding categories everywhere. So there's this whole field of applied category theory. There's just a summer school and like a conference that had like hundreds of people at it. And so, quantum computing uses a lot of category theory. Anyway, it's sort of an explosive growth phase right now, trying to apply abstract nonsense, which is kind of a funny like double negation. But anyway, enough philosophizing, or rather, let me open it up to the audience. Any questions or comments on the introductory remarks here?
Yeah, that's one of the best summaries I think I've heard, actually.
Well, thank you. On that note, we will post the recording for anyone who wants to watch it again. Other questions, comments? All right. So zooming in a little, since presumably, or I, based on people's comments, it sounds like there's a strong computer science bent here. Although for natural scientists, David Spivak wrote a great book, Category Theory for Scientists. But what are some categorical concepts that programmers here might have encountered? And so if you're into functional programming, if you ever heard the word Haskell, you probably heard the word category theory, even though the great irony is that as implemented, Haskell is not a category because it has to exist in the real world, shall we say. Monads, of course, is the big concept in Haskell that's related to category theory. But the whole field of type theory more generally is basically, you can think of type theory as being like the syntax for category theory semantics in a certain sense, or at least that's one way that I like to think about it. But there's category theory for concurrent computation, things like the pi calculus and such have categorical semantics. Use category theory to define data types. That's something we'll get into in these slides, like to actually say what it means in Haskell when you say like what a list is or what have you. That's what category theory is used for. Of course, much harder when you have like, a list is in Haskell, a list is not a list. It's kind of funny. We'll get into it. But anyway, there's a lot of applications of category theory, at least to computer science research and understanding, and we all hope to direct engineering practice in the future. So